Hi guys. So today we are doing a Euclidean problem like usual. So this one is quite different a little bit on the last question of 6.2.3 whereby we will be now proving an isosceles. So this is going to be an interesting one. Let's read the question statement. The question statement states Vn and Vy are tangent to circle or to the circle at n and y. Okay, so those are the two tangents that we have. A is a point on the circle, and an, a y, and ny are chords. So that angle A is equal to 65 degrees. Now S is a point on AY, so that AN is parallel to SV. S and N are joined. Alright, I don't know if it's me, but I felt like there was a lot of information back then, yeah. Okay, so 6.2.1. The first thing that we need to do, honestly, before we even begin to do anything, by now everyone should be knowing how we solve these problems. You have to write what? Dr. Cape Town. Exactly, because it is important that you know what to do before. A lot of students in the exam, right? They don't fail because they don't know the question. They just don't know how to approach it. It's like in life, you get scared to approach things, but it's fine. Okay, let's get back to your question. Now, since we've written Dr. Cape Town, we're going to analyze what we have. Do we have a diameter here? Now, let me give you guys a tip so that we can make this much quick and less stressful. Immediately when in the question statement they don't state anything about a center, and even you yourself you don't see a dot here, then there's no diameter. Okay, a diameter and a radius are not included if there's no if there's no if they didn't even tell you anything about the diameter. That's what I'm trying to say. So no center, no diameter and radius. Okay, so there's two on it here. Now, do we have a cyclic quad? Did they say anything about a cyclic quad, guys? I don't know. What do you think? No. And even you yourself, you can see here that there's no cyclic quad. And from the previous video, whereby we dive deep into the BBE method, we know that what type of cyclic quad we would be looking for. Now, is there a box type of a cyclic quad? A box type of a cyclic quad is the one of a supplementary. This one. Just a quick recap for those who haven't seen the video. And a bow tie, which is this one, and is an extension. This is an extension. Okay. All right. Now, I want us to now look into this question. All right. Sorry about that. Let's look into this question and solve it. Okay, so do we have a cyclic quad? Let's get back to this one and finish it. No, we don't have a cyclic quad. Do we have parallel lines? Yes. Do we have tangents? Yes. Okay, so we have two things, two theorems. Now we know we're going to be playing what with the tan chord and the parallel lines, and corresponding alternate, those type of things. Now the first question is write down with reasons three other angles which equal to 65 degrees. Okay. Now, when they say which equal to 65 degrees, they don't necessarily mean that you need to solve the other angles, and get other values. They want you to get the other values of the angles which are equal to 65. Simple. So the first thing that we're going to do, we're going to say we have parallel lines, right? So let's denote those parallel lines to make it easier. We're going to use a highlighter because I think it's much easier. We can work on it. So these are our parallel lines. Let me try and reduce the thickness a little bit. Yeah, okay, I think it's much better now. Alright, so this is the parallel line. This is the parallel line. You can even do it with your marking pen. Now okay. So if it's a parallel line, then this is the F, right? Then this means since you see the F, S1 is equals to what? 65 degrees. So F1 is done, so angle S1 is equals to 65 degrees. What is the reason? Corresponding angles, exactly. corresponding angles, right? Of which lines AN is parallel to SV, right? Good. My handwriting is bad. But then I'm improving, guys. Don't worry, I'm improving. Now, since we've done that, we've seen the parallel lines. It's important that you denote them so that you can see where they are and be able to see the alternating and stuff, right? Now we are going to be moving to the tangents. Now we have two tangents here, and we're going to use what? Tangent. Okay, so let's use tangent. Let's remove this and use tangent. So you're going to say tangent alternate back home. So this means that y3 is equals to 65 degrees. Okay, angle y3 is equals to 65 degrees using tangent. Now for the second one, we're going to do the same and say tangent alternate back home. Then this means that n1 is equals to 65 degrees, right? Tangent. Now we're moving to 6.2.2, and which states that prove that prove that VYSN is a cyclic one. Okay, so they want us to prove it that VYSN is a cyclic one. Okay, cool. Now immediately I'm sure someone is screaming on the screen right now. It's like, I have the answer, but I see the answer. And which you're correct. You know, this is the answer. You know, the answer is what? A bow tie. Okay. So as long as we can connect S2 and S and Y1 or Y3, I mean this and this, we have done it. Okay. So let's go back to your drawing board. Firstly, let's see what is Y3 equal to. Y3 is equals to Y3 is equals to 65 degrees. And what is S2? We don't have S2. Okay. Okay. N1 and S1, are they equal to each other? Yes, it is. So the reason why I'm doing this now, guys, it's because I want us to be sure that we don't have a simple way to do it before we do the tough calculations in order to find the angles, you know. So since I know that angle S1 is equals to angle N1, right, because both of them are equal to 65 degrees, then I can say that VYSN is a cyclic quad. Is a cyclic quad. What is the reason? The reason converse, or should I say YV, let's just say YV, yeah. YV subtends equal angle, right? Or you could just say angles in the same segment, yeah. Subtends angles, right? Now let's move to the last question, which is 6.2.3. I'm sure someone has already done this question, but then let's do it quick. Now they want us to prove that ASN is an isosceles. Now this ASN, they want us to prove that it is a isosceles triangle. Now how are we going to do that? Now we do know that an isosceles triangle, both of the opposite angles are equal to each other. Okay, so we just have to find that one. Okay, now since we proved that before, we proved that there's a cyclic quad here. Now we can use that cyclic quad to our advantage. So the first thing that I want us to look at is S2. Angle S2 is equals to Y3, right? Y angles in the same segment. Okay, guys? So this is equal to this. I'm just talking through the problem before I write it down. So it's equal to 65 degrees. Now we do know that N3, which is this one in here, it's equals to what? It's now going to be equal to 65 degrees. Why? Alternate angles. The importance of a marker. Right? Now if this one is equal to 65, both of them are equal to 65, then you're done. Side opposite equal angles. So let's write it quickly right now. Let's do it now. So let me write down what I said. What I said is angle Y3 is equals to angle S2. So it's 65 degrees. Angles in the same segment. Right? And this and this. And from there on, angle N3 is equals to angle S2, which is equals to 65 degrees. Reason? Alternate angles. Alternate angles what? Which ones? This one. SV is parallel to AN. Right? Cool. Now, since that is equal, this means that angle A is equals to angle N3. Therefore, I wrote it in the wrong place. Therefore, AS is equal to SN. Reason sides opposite equal angles. Then you're done. So this brings the end of this question, guys. It was a short, interesting question. It wasn't that long, and I hope everyone learned something in the end. And I'll see you guys in the next one.